Welcome to the final video in this module on sets and functions. You've come a long way and learned a lot since we first introduced the set 10 videos ago. Take a moment to congratulate yourself. In our final video, we're going to look at 5 special functions that are really important and useful in computer science. We're going to look at their definitions and how they're implemented in Python 3, and also look at their properties as functions. The first 2 of these have to do with rounding. Since we work so often with integers, it's helpful to have functions on hand that will take a number that isn't an integer and turn it into one that is. The simplest way to do that is by rounding. There's 3 ways to round, as you know: rounding off, rounding down, or rounding up. Computer science makes particular use of the last 2. The function that implements rounding down is called the floor function. In mathematical notation, it uses brackets like this with horizontal pieces on the bottom or on the floor. The floor function simply takes in a real number as input and rounds it down. It outputs the greatest integer that is less than or equal to it. For example, the floor of 2.9 is 2. The floor of negative 2.9 is negative 3, because negative 3 is less than negative 2.9. If you input an integer to begin with, there's nothing to round, so it just outputs itself. As a function, the domain of the floor function is the set of all real numbers, and the codomain is the set of integers. This function is not injective because there are a lot of collisions. In fact, any 2 numbers that are in between 2 integers will map to the same thing. For example, the floor of 5.4 and the floor of 5.8 are both 5. But the floor function is surjective because if you start with any integer in the codomain, you can find something in the domain that maps to it. For example, the integer itself will map to it. A companion to the floor function is the ceiling function, which rounds up instead of down. The ceiling of x is defined to be the smallest integer greater than or equal to x. The mathematical notation is similar to floor, except the horizontal parts on the brackets are at the top, or the ceiling. For example, the ceiling of 2.9 is 3, and so is the ceiling of 2.000001. The ceiling function is also a mapping from the real numbers to the integers. The example we just saw shows you that this function, like floor, is not injective, but it is surjective for the same reason that floor is surjective. Given an integer in the codomain, you can always hit it by plugging in just the integer itself. The floor and ceiling functions are available in Python, but they're not part of the standard library of functions that Python loads by default. To access them, you'll have to load the math package, which is a library of common mathematical functions. To do this, enter import math. Once this library is loaded, you do not have to load it again unless you restart Python. And then to call the floor function itself, type math.floor and then the input in parentheses. Ceiling is also in the math library, and it's accessed by math.ceil, C-E-I-L, and then the input in parentheses. And here are some more examples of its use. Here's a function that we're going to get to know extremely well in Module 4. It's called the factorial function. This is a function from the natural numbers to the natural numbers defined like this. We use an exclamation point after the input to denote it, and we define 0 factorial, which is how this is pronounced, to be equal to 1, and if n is a natural number bigger than 0, we define n factorial to be the product 1 times 2 times 3 times 4, and so on all the way up to n minus 1 times n. So in other words, n factorial is the product of the natural numbers from 1 to n, unless you're looking at 0 factorial, in which case that's just defined to be 1. So for example, 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. The factorial function can also be defined recursively, which means that we define it by calling the function on smaller versions of itself. Just start with an initial condition 0 factorial equals 1, and then we define n factorial to be n times n minus 1 factorial. In that way of thinking about it, for example, 5 factorial is 5 times 4 factorial. But then 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. And 1 factorial is 1 times 0 factorial, which finally, that's equal to 1. This gives us the product we saw earlier. This recursive definition is extremely important and handy for counting arguments, as we will see in great detail coming up soon. It also helps you to see an important fact, that the factorial function is strictly increasing. That means every time the input increases, the output also increases. And that means that the function would have to be injective, because for different inputs, you must get different outputs. The factorial function is not surjective because, for example, nothing maps to the number 4. The factorial function is available in Python 2, also in the math library, by typing math.factorial and then the number in parentheses. For example, here's 5 factorial, and we can easily make a little table of factorial values from 0 through 10. As you can see, the factorial function grows extremely fast. We'll be using the factorial function for counting purposes. For example, we will be learning soon that n factorial is the number of ways to arrange a list of n distinct objects. And that's why 0 factorial is defined to be 1, because there's only one way to arrange an empty list of objects, and that's to do nothing. Finally, there are 2 special functions related to division. One of these you've already seen, and that's the modulus function. We used a % symbol to represent it, and it's a function that takes in a pair of numbers, 1 an integer and 1 a natural number bigger than 0, and then returns the remainder we get when we divide the first number by the second one. As a function, this means the domain is the Cartesian product of the integers with the set of positive natural numbers, and the codomain is the set of all natural numbers. This function is not injective. For example, the pair 0, 10 and the pair 10, 10 both map to 0. But it is surjective because if we start with a natural number in the codomain, I can, for example, plug in that number mod that number plus 1, and this produces the number I started with. And going along with the mod operator is the div function, which does kind of the same thing as mod, except it returns the quotient instead of the remainder. There's not really a symbol for this function, and many people just write div of AB to mean the quotient we get when dividing A by B. For example, div 100, 5 is 20, whereas 100 mod 5 is 0. In Python, we can access these 2 functions, mod and div, without loading any libraries. The mod function, as you know, is accessed using the % symbol. Div, on the other hand, is implemented using a double slash like this. In Python 3, this means integer division. So if you write 15 divided by 4 with a single slash, you get this floating point number. But 15 with a double slash 4 gives me 3, just the quotient. A very important note here, in Python 2, the previous version of the language, the single slash denoted integer division. This was a major change between Python 2 and Python 3, so just be mindful of which Python version you're running. And that's a wrap for Module 3. In Module 4, we'll be putting all of our knowledge of sets, functions, and logic to work on solving problems where we are counting complex arrangements of things. This is a lot of fun, and I can't wait to see you there.